So we have talked so far about, these are important Taylor series, e to the x, sine x, and cosine x. I will expect you to know these Taylor series. We're going to use them often, and I will just refresh our memory here. The series for e to the x looks like, 1 plus x plus 1 over 2 factorial x squared. 2 factorial, of course, is equal to 2, so if you like, you could write 1/2, but I usually write the factorial in there just so that it's clear what the pattern is. All right, e to the x is all the powers of x with 1 over whatever factorial in front of it. Sine of x is only the odd powers, and they alternate the signs. So this sine of x is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5 minus the next one, and so on. Right? That's the Taylor series for sine of x. It's too small. Cosine of x is similar, only it's the even powers, starting with 1, and then minus the x squared term plus the x to the 4 term minus the x to the 6 plus etc. All right, these are like the 3 main Taylor series that you should know. Maybe just for fun, I mean, you should also, of course, know this, 1 over 1 minus x. This maybe is a complete list of all the ones that I would expect you to just straight up have these memorized. The first one, hopefully you already know. Those next ones we talked about last time. All right. As I have been saying, historically speaking, when people discovered the power series, they immediately were able to learn new things about these functions, or at least new ways of explaining things that they already knew. Like, for example, you can tell very easily by looking at the series that sine of 0 must equal 0, because if I plug in x equals 0 here, everything over there is 0. But cosine of 0, when I plug in x equals 0 here, you get 1, right? A lot of the basic properties of sine and cosine can be deduced from the series itself, even if you don't know anything about sine and cosine. It's also true that if you were to look at the sine and take the term-by-term derivative of everything here, when you take the derivative of x, you get 1. When you take the derivative of that, the 3 would come down, cancel the 3 in the bottom, and you would get this. Actually, each derivative term of sine gives you cosine. This is actually a very nice looking proof of why the derivative of sine equals cosine. Everybody get the paper? I would like to point out another very interesting, I would say very interesting thing that you can see here. You will notice the sine has only odd powers, the cosine has only even powers, and something I mentioned last time is if you added these two together, you would actually get all of the powers, and it would look like e to the x, although not exactly like e to the x, because the signs, the plus minuses would be wrong. You'd get like a plus 1 plus x, but then a minus, and then a plus and a plus. But I would like to check it out. Everybody satisfied with the list? Okay, thank you. This is a crazy fact that was discovered by a mathematician named Euler. This person's name is pronounced Euler. This is a German name. Don't say Euler. You will sound foolish. They will tell you, I have a boyfriend, if they hear you say Euler. It's Euler, or I have a girlfriend. A crazy fact that was discovered by Euler. Check it out. Surely everybody knows about I, the imaginary number, which is defined to be the square root of -1. Perhaps you've heard of I. It's an imaginary number. It's not a real number. Does that mean that there's no such thing as I? No, it's just like we just call it an imaginary number versus a real number. In the case of like the real world, I have my doubts actually whether or not real numbers actually even exist in reality. I don't really know. Like I think the number 3 maybe exists in real life, but something like, I don't know, some weird real number with non-repeating decimals. I don't know. Anyway, imaginary numbers are just as real numbers. They're just called imaginary numbers. They're still like a real thing that you can talk about. Anybody ever thought a little bit about this? Can anyone tell me what is I squared? I would say, yeah, this is root minus 1 times root minus 1. This ought to be minus 1, whatever that is. The whole point of I is that it is the square root of negative 1, which means when you square I, you should get negative 1, right? Okay. What about I cubed? This would be I squared times I, right? And I squared is negative 1, so this should be minus I. I don't know if you've ever thought about this kind of a thing. I'm not going to go crazy with this. What about I to the 4? This is the last one I'm going to say. Well, that should be, what should it be? It should be I squared times I squared, right? And that's 1. I squared is negative 1. So this is minus 1 times negative 1, which is 1. Okay, so I is I, but I squared is negative 1. I cubed is negative I to the 4 is 1. That means I to the 5 actually equals I. Like this is sort of a repeating pattern here. If I to the 4 is 1, then I to the 5 would be I to the 4 times I, which is I. All right. Anyway, this is not the crazy fact. I'm just refreshing our memory about the i's and such. I to the 4 is 1. I to the 5 is I, etc. All right. The I has a kind of alternating pattern. The signs don't exactly alternate. They go sort of positive, 2 negatives, and then 2 positives, and then 2 negatives, and so on. Check it out. What if we do, let's try e to the ix. So I'm going to use the series for e, but instead of x, I plug in I times x, just for fun. Let's see what happens. So the series looks like 1 plus, I'm writing the series for e. I'll just write the first 4 terms maybe. Ix cubed, 1 over 4 factorial, ix to the 4, etc. If you've never seen this before, this is kind of like, in my opinion, kind of mind-blowing what was discovered when somebody was trying to play around with this. Can we simplify at all? So I'm going to try and like resolve those parentheses. So I suppose this just looks like ix. You can't really do anything with that. 1 over 2 factorial. What can I do with ix squared? Well, you can kind of distribute the exponent and you get I squared x squared, right? So this is I squared x squared. 1 over 3 factorial. I cube x cubed. 1 over 4 factorial. I to the 4 x to the 4, right? Etc. And then based on what we said before, I would like to simplify those powers, the various powers of I. So this is ix, 1 over 2 factorial. I squared is negative 1. So actually, sorry, can I write this instead as minus 1 over 2 factorial x squared, right? Because I squared equals negative 1. I cubed, remember, equals negative I. So the next term is also a minus. And now it has, I'll put the I first. I, 1 over 3 factorial x cubed. Right? The next term has I to the 4, but I to the 4 equals 1. That's what we said before. So the next term is a plus 1 over 4 factorial x to the 4, and so on. All right? How am I doing so far? This is just sort of simple tricks. Now is the interesting part, or maybe. I'm going to separate out some of these in the sum here. Some of the terms are real numbers and some are imaginary. Like the ones with i's in front are imaginaries and the others are real. So can we just sort of separate out into 2 pieces? The real, this is, they call this the real part and the imaginary part. The real part is minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4, etc. Right? Those are the real ones. And then I'll say plus, and for the imaginary ones, I'm going to factor out the I. And then write what you get left over when the I gets factored out. So I had the original first imaginary one was ix. I factor the I, we get x. And the next imaginary is this one, negative I 1 over 3 factorial x cubed. So this is minus 1 over 3 factorial x cubed. All right, etc. I only wrote up to the degree 4 term, but the patterns are very easy. You could work this out to more terms if you really wanted to. All right. Anybody recognize anything here? Notice anything about this business? I see this. Does that look like anything? It is. Cosine. That is this is the series for cosine of x, and this is the series for sine of x. I didn't write very many terms, but if you're curious, you could write out more, and you'll see that it matches the series. So this is cosine x plus I sine x. All right. If we read it all together, this is a true formula. So e to the ix equals cosine x plus I sine x. This is a true fact. I'm not making this up. This was discovered by Euler. At least that's what people typically say. You know, historically speaking, it can be hard to tell sometimes. This is sometimes referred to as Euler's formula or Euler's theorem, although there's a lot of things called Euler's theorem. What it shows is there is a deep relationship between the function e, like e to the x, is related to sine and cosine in this very weird way. In my opinion, this is, I said this is kind of mind-blowing. It's the reason that I think that this is mind-blowing is because if you just think about, like, historically speaking, when these various mathematical concepts were created and for what reason, like sine and cosine were created in order to do trigonometry. Like ancient people were using something like sine and cosine, thousands of years ago. This function e was created like in a fit of capitalism. Like this arose first when people were talking about compound interest, but of course it represents any kind of exponential growth. This function e to the x really ought to have nothing to do with the trig functions at all. They are intended for completely different purposes. They were invented by people in vastly different like historical periods and cultures. And the number I, if you even want to call it that, was also the product of a very different type of mathematical culture. The number I was created by people who were just beginning to start to do some kind of mathematics which wasn't immediately applicable to real life. That is yet another level of mathematical development. Anyway, the fact is that these three things are all related in this fairly simple formula. There is no real good reason why that ought to be true. It just is true. It is a profoundly surprising fact, in my opinion. And sometimes people like to wonder about, like, why are things like this true in mathematics? Usually when you ask people sort of like, why are mathematical formulas true? I think one answer to that is mathematical formulas are true because we invented them in order that they would be true. Like if there were somehow like math formulas that didn't work, we just wouldn't talk about them because they wouldn't be useful for anything. Like the reason why we do mathematics is because it's true and useful. But this is a fact. This is a true fact about mathematics, which was not. It was not intended by the creators of e to the x or cosine or sine or anything like that. Very weird. Something you can get a little fancier about this if you just plug in that in the box there seems pretty abstract to me, but here's another little trick. Let's plug in x equals 0. What does it say? Sorry, not 0. That's not very interesting. If you plug in 0, you get 1 on both sides, which is not terribly interesting. I'm going to plug in x equals pi. On the left side, it says e to the I times pi, which is just some ridiculous thing. This, to me, this looks like, I don't know, a kid at the soda machine who just like takes a little bit of everything. Like, this is just like, take all your favorite numbers and just like throw them together at random, all right? What do you get on the right-hand side, though? It equals cosine pi plus I sine of pi. And that actually we can simplify. Anyone, what's the cosine of pi?
Negative.
It is -1. Yeah, cosine goes down like that, right? This is pi. So this is -1. And the sine of pi?
0.
Yeah, sine of pi is 0. That's this one, right? So that's it, actually. It's right here. Huh? This is like the kid randomly combining things in a ridiculous way at the soda machine. Actually, you don't get a ridiculous answer. You get a very ordinary looking answer. This is, again, I don't know if you are able to appreciate in the way that I do, but this to me is a profoundly mind-blowing and beautiful fact about, I mean, it's really a bizarre fact about numbers. One way that people like to write this formula, just by, if you add 1 on both sides, it says this, e to the I pi plus 1 equals 0. And I believe this is written on Euler's tombstone. And, you know, a lot of people have like tattoos of this and things like that. This is generally, so this is called Euler's formula, and this is generally regarded as the most beautiful formula in mathematics. This is like, if you ask people in general, this is like the go-to answer. This is kind of like the Beatles of mathematical formulas, all right? Some people will, some sort of hipsters will say, oh, no, you gotta check out this other thing. But really, on some level, this is the thing that everybody acknowledges as like the goat of all mathematical formulas, all right? Because, why is it so goated, as they say? It's because if you ask me, like, what are like the 5 most important numbers in mathematics? I would say, okay, you got to go 0 and 1 because that's the basis of all the counting numbers. Of course, you got to go pi because that's kind of like the most fundamental number in geometry. I would take e because that's the most fundamental number in calculus. And then I would also take I as the most basic number in like complex analysis or in algebra of you know, non-real numbers or whatever. But anyway, if you take all of those numbers, again, they should really, there's no reason that they have anything to do with one another because they were all created in completely different contexts of mathematics, apart from maybe 0 and 1. But anyway, you can put them all together in this formula and you get something that makes sense. This is deeply strange in my opinion and really quite beautiful. And if you ask me, like, I don't know if you really care, but like me personally, what interests me about mathematics is this kind of a thing. I am, in my own like mathematical research, I actually don't do any kind of math that is useful in real world. And you may have noticed, I don't know if anybody noticed, we have like never ever done an applied problem this whole semester. I don't know if you missed that kind of stuff, but that's, I don't necessarily feel good about that, but that's probably just because of my own point of view. Like that kind of thing just doesn't make me very interested. But this kind of thing does. There's a famous quote by a mathematician named Ramanujan, who was an Indian mathematician at the beginning of the 20th century. He said, "For me, a mathematical equation has no meaning unless it represents a thought of God." And I kind of feel the same way. Like to me, I hear God speaking when I see this. Rather than something like the quadratic formula, it's like, okay, that's cool, but like, I don't know, I hear some physicist speaking or something like that. To me, this is somehow far more profound, and this was not invented by some guy trying to solve a problem. This just straight up is true, like for no good reason. That to me is really very, very deep and worthy of my admiration. I don't know if you feel the same way. This is all I'm going to say about it. Anybody have any thoughts about that? I don't need to just tell you my opinions about things. All right. Interesting. Here's another there are interesting and actually there are useful ramifications of this. So one thing that you get for free, here's sort of more formulas, and I'll just leave it at this, and then we'll get back to some nuts and bolts of Taylor series. More formulas based on this. I don't know if you've ever seen this before, but if you look at a big list of trig formulas, you probably learned a bunch of them in high school. Here's one that you likely have not seen before, but this is a true formula about sine of x is equal to e to the ix minus e to the minus ix over 2. Now, if you didn't already know this Euler's formula, you would say that looks completely ridiculous, and how could that possibly be true? But I don't need to go through a derivation, but this is actually fairly easy to show that this is a true formula based on this e to the ix thing. And there's a similar formula for cosine. It's just the same but with a plus. Plus e to the minus ix over 2. These are true formulas about sine and cosine. And those formulas are actually useful from time to time. I mean, they're kind of obscure, but they do come up and they are useful in working with sine and cosine to sort of transform sine and cosine into e's. I'm sure you can imagine there are some situations where it would be more convenient to work with e's instead of sines and cosines. And you can just straight up change one into the other. Like there's a certain sense in which it's kind of like you have sine and cosine as the basic trig functions, but sort of like e is kind of also a trig function in this way. It's just one which has like imaginary numbers plugged into it. Very strange. I think that's all I want to say about that. For the remainder of our time together, which is the rest of today plus a little bit tomorrow, I just want to talk about finding Taylor series for other kinds of functions. So you should, like I said, basically have these ones memorized. I suppose you should memorize them in time for our test. You should remember those ones. And then you can build Taylor series for other functions as variations of those basic ones. So, I wanted to do one more example just because we did not ever do an example like this last time, but let's just try one. Finding Taylor series not centered at 0. All right? Last time, all the examples we did were centered at 0, and I just wanted to do one where it's not centered at 0. So remember, the format of such a Taylor series looks like this. They are coefficients in front of things that look like powers of x minus a, where a is the center. And if I ask you to find the series, really what I'm asking is find those coefficients, and those coefficients are given by, this is what we call Taylor's theorem, 1 over n factorial, f the nth derivative at at a, not x minus a. All right. Usually we use a equals 0, which makes all the formulas a little bit easier, but you can do it with other values of a, and I thought we should just do at least one of them like that. I forgot to mention, I am going to make one last homework assignment just about the Taylor series, just so that you have some idea of what what I expect you to know for the last quiz question and test. All right, so let's find the Taylor series for sine of x centered at pi over 2. Let's try that. All right, the one that I drew before and put in the box and said you should memorize this, that was the one centered at 0. But we should be able to do this centered at pi over 2, just as an example. So really, I mean, the answer is going to look like this with pi over 2's in it. Really, the only thing that we need to work on is what are the coefficients, right? So we need to find Cn, which is 1 over n factorial, f the nth derivative at pi over 2, right? And this is the hard step, I guess. I mean, it's not really hard, but you have to figure out what these derivatives are, the nth derivative of f, and then plug in pi over 2. So towards that end, remember my function is sine of x, so f of x is sine x. F prime of x, I'm just going to write down some derivatives here, and hopefully we will eventually be able to deduce a pattern. The second derivative, the third derivative, let's just go up to the fourth, and then hopefully we'll be able to figure out what's going on by then, right? You take the various derivatives of sine x, which is not hard. It becomes a cosine, and then negative sine, and then negative cosine, and then back to sine again, right? Those are the various derivatives of sine x. And then we're going to plug in because of this, right? I want to do f the nth derivative evaluated at pi over 2. So when I do f of pi over 2, I'm going to do f prime of pi over 2, f double prime pi over 2, and so on. What's that? That's sine of pi over 2. Any trig masters out there? What do you say?
1.
It is 1, yeah. Sine of pi over 2. I don't know how you like to remember this, but here's pi over 2. This is how I remember this, by remembering the graph of sine. Sine of pi over 2 is 1. And the graph of cosine goes like so, and you get 0. So actually, that's the next one, right? F prime of pi over 2, that would be cosine pi over 2, which is 0. F double prime of pi over 2, that would be negative sine pi over 2. That's negative 1. F, the third derivative, pi over 2, that is negative cosine pi over 2, which is 0, because cosine pi over 2 is 0. The fourth derivative, that would be sine of pi over 2 again, which is 1 again. So these things, they alternate, or it's not technically alternating, but they sort of cycle. 1, 0, negative 1, 0, 1, and then it continues from there. All right. We now have enough information to say what the constants are, right? They are 1 and then 0, and then negative 1 and then 0, and then 1 and then 0, and so on. So what we have here really are, I guess, the even derivatives. The second derivative, the fourth derivative, you could say this is like the 0th derivative. They are non-zero, and they go 1s and minus 1s, all right? So we'll get only the even terms. All the odd ones are 0, right? The first derivative, the third derivative, and so on. And can I say like so? So it'll say sine of x equals only the even terms. So the first term will be a 1, and then plus 0, x minus pi over 2, plus. The next term looks like 1 over, sorry, it's not plus, it's minus. 1 over 3 factorial. And then I say x, what am I talking about? 2 factorial. It's 2. The degree 2 term has a 2 factorial in front of it. X squared. The reason I put a minus is because this coefficient was minus. And the reason I put the 1 over 2 factorial is because the Taylor series always includes the 1 over the whatever factorial. All right? The next term will, and it's not x squared. It's x minus pi over 2 squared, because I'm doing the series centered at pi over 2. All right, the next term, the cubic, the degree 3 term is a 0. So this is going to be 0, x minus pi over 3 squared to the cubed. The next one will be plus 1. This is the 4th degree term. So it'll say plus 1 over 4 factorial x minus pi over 3 pi over 2. I'm sorry, I'm really like that. All right. If I wanted to write it without the zeros, it would just be 1 minus 1 over 2 factorial x minus pi over 2 squared plus 1 over 4 factorial x minus pi over 2 to the 4 minus. The next one will be minus 1 over 6 factorial. I can tell what the pattern is at this point. X minus pi over 2 to the 6, and so on. All right. That's my Taylor series centered at pi over 2. It's just a matter of calculating the coefficients slightly differently. I plug in pi over 2 every time instead of plugging in 0 every time. All right. Interesting fact, this looks kind of like cosine to me because it has only the even ones and it begins with a 1. That's actually because sine of x plus pi over 2 is equal to cosine of x. There's some property like that, and that's why this looks like cosine basically, because it's the same as sine, but I shifted all the x values by pi over 2. Right? Excellent. This is how to find the series centered at some other point. All right. What I want to do, we got 15 minutes left. I would like to just talk about some more tricks for finding series. And these are actually the same tricks that we've been using, so this is not no big surprises here. Only we haven't used them really to find Taylor series. I will first of all just write again. These are like the basic ones that everybody should know. 1 over 1 minus x, 1 plus x squared. This is the easiest one of all. Then we have e to the x, which is every term in there, all the powers with the factorials in front. Then we have sine of x, which is only the odd powers, x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5 minus etc. And then the cosine is only the even powers. All right, so these ones. Start with these. You can do what I have in the past referred to as simple tricks to get Taylor series for other more complicated functions. All right? So, for example, let's do tricks to find Taylor series for something like x times sine of 2x. All right? Now, without tricks, I mean, just doing it in the same way that we just did that example, the way to find the Taylor series is by taking the derivative over and over again of this function. You have to take the first derivative, and then the second derivative, and the third derivative, and so on, and then plug in 0 or whatever. Now, this particular function is a total nightmare to do that, because to get the first derivative, you have to use the product rule with the x and the sine of 2x. And so the result of the first derivative would be actually not just one thing, but two things added together, because you do the product rule. And then to get the second derivative, you have to do the derivative of that again, which would be still more complicated. So actually this function gets increasingly more complicated every time you take the derivative. And this is a real nightmare to find this series of. Instead, we can use simple tricks. And that is, my trick will be plug in 2x for the series of sine x, right? So that's the first trick to deal with sine of 2x. You can just use this series here, which you have memorized, and just replace all the x's with 2x, all right? And then to get, instead of just sine 2x, to get x times sine of 2x, you just take one extra factor of x and distribute it across the series, all right? So I'm going to plug in 2x for the series of sine x, and then distribute, well, I'll just say multiply by x. All right. You'll see what I mean. This is not so difficult and much easier than finding the Taylor coefficients directly by taking derivatives over and over again. That you want to avoid that whenever possible, because that is difficult. So first of all, I'm going to say sine of 2x. This is not my final answer because I really want x sine of 2x, but as a preliminary step, what is sine of 2x? I'm going to plug in the series that you see at the very top, sine of x, but use 2x instead of x. So it says 2x minus 1 over 3 factorial 2x cubed plus 1 over 5 factorial 2x to the 5. Make sure you get your parentheses in the right spots there. And then we're going to simplify. I want to still write it like a power series with, coefficients in front of powers of x. So those various exponents, you need to kind of distribute them. Anyway, I get 2x from the first one, but the next one I will write as 1 over 3 factorial times 2 cubed x cubed. And you could write 8 if you want. I think it's a little clearer to just leave it as 2 cubed because I don't want to deal with actually working out all of these powers of 2. 1 over 5 factorial, 2 to the 5, x to the 5, all right, etc. So that is sine of 2x. All right, as far as what I said I was going to do at the top, it says plug in 2x for the series of sine x. I just did that. And then multiply by x. So, and this is also easy to do. X times sine 2x then apparently equals x times all of this business. And as we've talked about before, if the series converges, you can just like multiply across it. You can distribute that x. So my final answer will say 2x squared minus 1 over 3 factorial, 2 cubed times x to the 4. I am distributing the x, so it just increases the power of x on each term by 1. Plus 1 over 5 factorial, 2 to the 5, x to the 6, and so on. This is the series of x sine of 2x. All right. Any thoughts about this? These are simple tricks for finding the series of whatever. All right. Can I have you guys try one, and then maybe that'll do it for us for today. I have a few more simple tricks, but I think we can pick them up next time. So how about you try series for e to the 2x over x squared. This will be very similar. You begin by plugging into the series for e, and then deal with that dividing by x squared somehow. I'm going to start writing my answer here. It looks like people are doing fine. As I was walking around, it looked like people are doing fine. So you should start by plugging in 2x to the series formula for each of the x, and then just simplify the exponents a little bit. And then finally, to get, this is e to the 2x. What I'm really after is e to the 2x over x to the minus 2. Maybe it's over x squared. It might be, I don't know, if you find it easier to think of this way, distributing x to the minus 2, or you could say divide everything through by x squared, basically has the effect of decreasing all the powers of x by 2. So you get 1 over x squared first, and then 2 over x, and then 1 over 2 factorial 2 squared times nothing, like x to the 0, and then 1 over 3 factorial 2 cubed x, 1 over 4 factorial 2 to the 4x squared, etc. That's what I got. I think that's pretty much what everybody else seemed to say. Can I do one more, just very quick example we got 5 more minutes left. Very similar trick, but look at, this is actually a little bit easier. How about sine of x over x? I find this one a little bit satisfying. Sine of x, of course, is just x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5 minus, etc., right? And so to do sine of x over x is that same thing, but I just decrease all the x exponents by 1. And so it's 1 minus 1 over 3 factorial x squared. You just decrease all the powers by 1. All right. What's interesting to me about that is, I don't know if this is something that you think about ever, but this is like a basic fact that you had to learn at some point in your youth about trigonometry, is that, remember, lim x goes to 0, sine x over x. This is 1. Although it's not really obvious why that's true, but actually you need to know that this is true in order to show that the derivative of sine is cosine or something like that. Now you could use L'Hopital's rule for this, but that's a bit of a, to explain why this is true, L'Hopital's rule is a bit of a sledgehammer in that case, because this is usually used as a justification for why the derivative of sine equals cosine. And if you are using L'Hopital's rule to prove that, that's kind of circular, because you'd have to take the derivative of sine. But anyway, what I'm saying is, if you know this series here, then actually this fact becomes obvious. Because up here, you can just straight up plug in x equals 0 and you get 1 as the answer. I think this is kind of cute. This is another, this is a very, not terribly deep, but fairly simple example of when sometimes looking at the series of a function actually makes things much easier to handle. And that's one example of that. All right, I think that'll do for today. So Friday we will have the quiz plus not a full class, more of Taylor stuff.